Hello students, welcome to the online lecture series of digital communication. We are studying unit number 3, that is random signal and noise. Before moving towards our today's lecture, let's have a quick revision what we have studied in last lecture. In last lecture, we have studied types of random processes, that is stationary random process and non-stationary random process. So how you define stationary random process? When the statistical properties of random process, they don't change with time, it is called stationary random process. Whereas when the statistical properties of a random process do change with time, it is called non-stationary random process. Again, we have categorized stationary random process into what? Wide sense stationary process, which is also called weakly stationary process, and ergodic process. After that, we have seen the statistical properties of random process. That is what is mean, what is autocorrelation, autocovariance. Then we have seen the mathematical representation, that how we are going to represent your stationary process, non-stationary process. Then we have seen wide sense stationary process. We say wide sense stationary process when it is not in strict sense. The random process, it is, or stationary process which is not in strict sense, it means just its mean and autocorrelation functions are independent of the shift of the time of origin. So that is called what? Wide sense stationary process. Then we have seen the mathematical representation of it. Now, today's topic, we are going to see what are ensemble averages, what are time averages. After that, we are going to see what is ergodic process. And then the important topic of this today's unit is what? Transmission of your random process through LTI filter. So let's start with our today's topic, that is ergodic process. Now, before moving to the definition of ergodic process, it is necessary to define ensemble averages and time averages. Now, what is ensemble averages? The expectation of or ensemble averages of stochastic process x of t, which is also called as random process, are averages across the process at a particular instant. So over here, mean and this autocorrelation functions are what? Ensemble averages. Now for the reference, you can see this graph. Basically, in our previous lecture, we have shown this, that it is an ensemble of your sample functions. It is nothing but your temperature of day 1 at time t1, then temperature on day 2 at time t1, temperature on day 3 at time t1, and temperature on day n at time tn. So basically, it is what? Sample function. Now what we are going to do it, the mean of stochastic process or this random process at some fixed time, suppose t1, small t1, it is what? A fixed time, which is nothing but what? Expectation of this random variable x of t that describes all the possible values of this sample function of the process which is observed at a particular instant t1. So what we are going to do it, we are going to take the mean across the process. So as we already defined that mean, it is a mu x t, which is equal to integration from minus infinity to infinity x of small f of x of t function of x dx. It is nothing but your mean. Similarly, the autocorrelation function, which is denoted by Rx t1 comma t2, which is equal to double integration from minus infinity to infinity x1, x2, f of capital X of t1, x of t2, which is a function of x1, x2, dx1, dx2. Or you can see this apart. X of t1, x of t2, it is nothing but what? A random variable at two instants, t1 and t2. That is a self correlation at a different instant, t1 and t2. So these two averages, that is mean and autocorrelation, which are taken what? Across the ensemble at a particular instant time. Hence they are called what? Ensemble averages. The next is what? Time averages. Basically these are the averages. It is called a long-term sample averages or time averages, that are averages along the process. Remember that ensemble averages what? It was across the process, but time averages are what? Along the process. So it is necessary to relate what? Your ensemble averages and time averages. Now consider the sample function small x of t of a wide sense stationary process capital X of t with the interval, that is small t, it should be greater than or equal to minus t and less than or equal to plus t. So therefore the DC value of this sample function x of t is defined by the time average. So this is time average is given by mu x capital T. Remember the mean of ensemble average, it is given by mu x of small t, but over here it is along the process with the interval minus t to t. So it is mu x of capital T, which is equal to 1 upon base over here it is what? 2t, because the integration it is from minus t to plus t x of t dt. So this is called what? Time mean, which is also called as DC value of the process. Now next is what? Time average autocorrelation function. Now this autocorrelation function is along the process, which is denoted by what? Rx tau t, and it is given as 1 upon base, that is 2t, because this is a sample function which is observed over an interval from minus t to plus t. So autocorrelation function Rx tau t is equal to 1 upon base, that is 2t, integration from minus t to plus t x of t plus tau dt. Now in order to define your ergodic process, it is very important to understand this ensemble averages and time averages. So in ensemble averages we have seen mean function and autocorrelation function. Mean, it is denoted by mu x small t, and autocorrelation is defined as Rx small t1 t2. But in time averages, see the ensemble average are what? Across the process, and time averages are along the process. So over here mean, it is defined as, it is given as what? Mu x capital T. It is over the period. And this is the autocorrelation function, which is also over the period from minus t to t. So that's why it is given as Rx tau t. So please remember this one, because in order to understand ergodic process, it is necessary to remember ensemble averages and time averages. Now, starting with ergodic process. So what is ergodic process? Basically, a random process or stochastic process is called ergodic process if time averages are equal to ensemble averages. That is, just we have seen that mu x of small t, it should be equal to mu x of capital T, that is a ensemble mean, it should be equal to your time average mean, and the autocorrelation function, that is ensemble autocorrelation function Rx T1 T2, it should be equal to what? Rx tau T, that is a time average autocorrelation function. So we have to define the ergodicity in two functions, mean as well as autocorrelation. So first, starting with ergodicity in mean, the process is ergodic in mean if following two conditions are satisfied. Now, what are those two conditions? So first condition is that limit capital T tends to infinity, mu x of capital T is equal to mu x of small t, which is nothing but just mu x. So basically this first condition says that time mean, this is time mean, it approaches ensemble mean as observational time interval capital T approaches infinity. Now what is the second condition? Second condition is that limit T capital T tends to infinity, variance of mu x of capital T, it should be equal to 0. So over here variance, that is mu x t, is treated as a random variable which approaches what? 0 in the limit as observation interval T, it approaches what? Infinity. So second condition says that the variance of time mean is 0 as the observational interval T approaches what? Infinity. So if these two conditions are satisfied, then we can say there is an ergodicity in mean. Now, we say that the process is ergodic in autocorrelation if following two conditions are satisfied. So the first condition is that limit capital T tends to infinity, Rx tau comma T, it should be equal to Rx small t1 t2. It means the first condition says that the time averaged autocorrelation function, it approaches ensemble autocorrelation as the observation interval T, it approaches what? Infinity. And the second condition is what? That is limit T tends to 0, variance of Rx tau T, it is equal to 0. It means the second condition says that the variance of time average autocorrelation is 0 as the observation interval T, it approaches infinity. So if these two conditions are satisfied, we can say that process is ergodic in autocorrelation. So hope you understood ergodic process. Now moving towards a next topic, that is transmission of random process through LTI filter, that is linear time invariant filter. Now this LTI system, basically it is characterized by impulse response h of t. It means that if impulse response, impulse delta of t is applied to it, then output would be what? H of t. So the input x of t, which is nothing but your random process, is applied as an input to this linear time invariant filter of impulse response h of t. So since it is input is random process, therefore the output y of t, it would also be a new random process which is produced at the output. So output of this filter, it is given as what? y of t is equal to x of t, which is convolved with what? H of t. This is nothing but your convolution operator. So make it as equation number 1. Now in general, it is very difficult to describe the probability distribution output of the random process y of t, even when the probability distribution of the input random process x of t, it is completely specified for suppose from minus infinity to infinity. So over here we wish to determine the time domain form of this input output relation of this filter. So this convolution operator, it is represented in time domain. So suppose assuming that x of t, it is what? Wide sense stationary random process, and to determine the time domain form of this input output relation of the filter, it is given as y of t is equal to minus infinity to plus infinity x of t minus tau 1 h of tau 1 d tau 1. So make it as equation number 2. Over here y of t is also what? A random process which is indexed by time t. Now to examine the properties of this random process y of t, we have to consider the functions mean and autocorrelation. So by first we would considering the mean of this y of t. So all the students please note down this equation, because in next we are going to use this equation. So along with this you also write it and note it down this equation. So consider first the mean of this output random process y of t, which is given by mu y t, which is equal to nothing but the expectation of the output, that is y of t. Now I just told by using that equation we are substituting the value of y of t. So it would become expectation of substituting the value of y of t, it is integration from minus infinity to plus infinity h of tau 1 x of t minus tau 1 d tau 1. Tau 1, it is nothing but over here it is a integration variable. As this expectation operator is linear, so we are rearranging this integration expectation operator. So we can write it that mu y of t is equal to integration minus infinity to infinity h of tau 1 expectation of this x of t minus tau 1 d tau 1. Make it as equation number 3. Now as we know this x of t, it is what? Wide sense stationary random process. So the expectation of this random variable, it is what? Nothing but it is a mean mu x, which is constant, which is independent of the time. So we can write it mu of yt is equal to integration from minus infinity to infinity. As we know the expectation of this term is nothing but your mu, which is constant mu x h tau 1 d tau 1. Now taking this term outside of this integration, we can write it mu y of t is equal to mu x integration from minus infinity to infinity h of tau 1 d tau 1. As we know, the Fourier transform of h of tau is nothing but your what? H of f. Now putting that if f equal to 0, then what we would get? We would get that equal to mu x h of 0. Over here this h of 0 is nothing but what? It is a DC response of the system, or we can say it zero frequency. So this mu of yt, it is nothing but just it is a mu x h of 0. So it is also not dependent on time, it is independent of time. So we can say that the mean of output process is equal to product of input process and the DC gain of this LTI filter, that is linear time invariant filter, and hence y of t is stationary in mean. Now, considering the second function, that is the autocorrelation function of this random process, output random process out of y of t, it is given by what? R of y tu is equal to expectation of y of t and y of u. Now what is this small t and u? It is nothing but your denote two values of the time at which output process is observed. Since it is a self correlation, autocorrelation, we are going to observe the output process at a two different time instant of time, that is at t as well as u. Now, using the convolution integral, we can write it that for y of t, expectation, what is y of t? It is nothing but what? Integration from minus infinity to infinity h of tau 1 x of t minus tau 1 d tau 1. Now putting the value of this y of u, integration from minus infinity to infinity h of tau 2 x of u minus tau 2 d tau 2. Make it as equation number 5th. Now this r of y tu, by rearranging this term as expectation operator, it is a linear over here, so we can rearrange this integration and expectation. We can write it integration from minus infinity to infinity d tau 1 or h of tau 1 d tau 1, second integration from minus infinity to infinity d tau 2 h of tau 2, or you can write it h of tau 2 d tau 2, expectation of x of t minus tau 1 x of u minus tau 2. It is equation number 6th. Now, as we know, the expectation of this random variables, it is nothing but what? Autocorrelation. So we can write it, that is integration from minus infinity to infinity, carry forwarding the same term h of tau 1 d tau 1, integration minus infinity to infinity d tau 2 h of tau 2. This is nothing but what? Autocorrelation. So we can write it rx t minus tau 1 u minus tau 2 and make it as equation number 7. Now, when the input x of t is wide sense stationary random process, then the autocorrelation function of x of t is only a what? Function of the time difference between the observation time at t minus tau 1 and u minus tau 2. So we can put it as tau equal to what? This t minus u in equation 7. So we would get, so we can write it that r of y, it is t minus u is equal to integration from minus infinity to infinity d tau 1 h of tau 1, integration from minus infinity to infinity d tau 2 h of tau 2 rx, that is this term minus this term. So it would be t minus tau 1 minus u minus minus plus tau 2. So we would get rx of, you can rearrange this term and you can write it as like t minus tau 1 minus u plus tau 2. It would be equation number 8. Since t minus u, it is nothing but what? Tau. So we can write it r of y tau. You can take this double integration from minus infinity to plus infinity h of tau 1 h of tau 2 rx, that is tau minus tau 1 plus tau 2 d tau 1, d tau 2, make it as equation number 9. So note down this equation. So from this equation, that is Ry of tau, this term basically autocorrelation of tau minus tau 1 plus tau 2, it is nothing but what? Independent of time. And also h of tau 1 and h of tau 2 are also what? Independent of time. So output r y of tau or t comma u will also be what? Independent of time. So rather it will be a function of what? Tau, that is t minus u. So combining the above result that involving with mean that we have seen for mean as well as this autocorrelation function, so we can say if the input to a stable linear time invariant filter, it is a wide sense stationary random process, then the output of the filter is also what? Wide sense stationary random process. So from the result that we have calculated for mean function and autocorrelation function, so if input to LTI filter is a stationary process, then output is also what? Stationary process. So we have seen that the mean and the autocorrelation function of this stationary process are what? Independent of time. It is what? Independent of time. So it is called what? Wide sense stationary random process. So we can say or we can state that if the input is wide sense stationary process, then output is also what? Wide sense stationary random process. So hope so you understood the topic, that transmission of random process through your LTI filter. So if in your examination this question it is asked, so you have to first tell the concept of this transmission and then you have to show this mean of output process and autocorrelation of this output process, and you have to tell that output of the filter is also a wide sense stationary process if the input to this LTI filter is wide sense stationary process. So guys, what is the summary of today's lecture? We have studied ensemble averages, we have studied time averages. That ensemble averages, these are the averages which are taken across the process, and time averages are the averages, long-term averages which are along the process. Then we have seen that what is ergodic process. That is, if ensemble averages are equal to time averages process, then that random process is called what? Ergodic process. After that, we have seen the conditions, that ergodicity in mean. What are the two conditions? We have seen ergodicity in autocorrelation, then also what are the two conditions that to be satisfied. After that, we have studied the transmission of random process through LTI filter. And we have seen the autocorrelation function and the mean function, and we have characterized that wide sense stationary process in what? Time domain relationship. So here it is your assignment number 10. So please note it down, this assignment. The next lecture's topics we are going to cover, it is a power spectral density of random process and properties of your power spectral density. Basically, this power spectral density we are going to see, today we have seen the input output relation of a filter in time domain. But for this power spectral density, we are going to see the relationship in frequency domain. So if you have any questions or feedback, you can post it on my email, which is given on this address. So it's all about our today's lecture, and we will see in next lecture. Thank you very much.